Yeah, in this lecture we're gonna learn more about what we call the direct substitution or the basic substitution method. So the first type, the direct substitution. Direct substitution. Direct substitution. So what we can do, so let's look at an example and see what's really happening here. So I'm going to say the motivation. So let's look at this problem. So consider the differential equation. So consider the differential equation. Consider the differential equation. Y prime equal x minus y plus 1 to the square. So let's say you have a differential equation like that. So you can see that this differential equation is kind of complicated. So what we can do is we can expand this. So if you distribute this side, so you're gonna get how to distribute a three-term expression. So if you want to, if you're going to square a three-term expression, what's going to happen is you're going to square each term, and also you're going to multiply two terms and also multiply by 2. So if you use that argument, you can simply write this one as x squared. You square each term. That's the first thing, and then you're going to multiply 2 at a time and multiply also by 2. So that means you're going to get negative 2xy, and then 2x. And then 2y, and then you can see that now this is the differential equation. So so it is clear that this is not of a basic integration problem. Remember what we talk about basic integration problem? You can just integrate the two sides, or you can make the one side upside down and integrate. But you can see that this is not a basic integration problem because there's a y term and x term both. So it is not a basic integration problem. So it is not of basic integration. And then is it separable? Can you separate this into the right hand side as a product of x and y function alone? And you can see that you cannot separate this into a product of x and y function alone. Okay, so that means this is not of separable. And is this a integration factor problem? So integrating factor. Is this an integrating factor problem? And you can see that there are y squared terms here. So since there are y squared terms, this cannot be integrating factor method. So that means it is none of them. So this problem cannot solve in any of those three techniques that we learned before. So that means we need a new technique. Okay, so need a new technique. Need a new method. Okay, need a new method. This new method is what we call the direct substitution. So let's look at the idea. So what we call use substitution method, or the direct substitution. Okay. And once you use the direct substitution, what's going to happen, then you're going to reduce this problem to a separable equation. Okay, so so what we normally call the reduction to separable method. Some people call it like that. So reduction to separable method. Okay, so so what we're going to do for this our particular problem, so what we can do, we're going to say let v equal the inside function. In our case it is x minus y plus 1. So that is the magic substitution that we're going to use. So if you go back, you can see that this is the inside function. So we're going to substitute for that. I'm going to call that function v. Okay, you're going to substitute for that. We're going to call this v. So that's always the case. We're going to substitute for the inside function. So once you do that, you can see yeah, so this is inside function. Okay, inside function. So if you do that, now what we do, we just take the derivative with respect to the independent variable. Okay, so take the derivative, with respect to the x. Okay, x is the independent variable, so we're gonna pick the independent variable. So once you take the derivative with respect to x, what will happen? This side become dv over dx. This is 1 minus this become dy over dx and 0. So in other words, we can write this one as v prime equal 1 minus y prime. So that means this one we can write y prime equal 1 minus v. So now what we can do, we're going to do two substitutions. We can substitute wherever you see x minus y plus 1, we can substitute for that v, and also wherever you see y prime, you can substitute 1 minus v prime. So we can do both substitutions. Okay, by substituting, our original differential equation now becomes so okay, let's write that. So we had y prime equal x minus y plus 1 to the square. Now what will happen? You can substitute. Once substitute for both sides, this side become 1 minus v prime, and this simply become v squared. And you can see that you can write this one as dv over dx equal 1 minus v squared, and you can see that this is a separable equation. This is separable. Okay, so that means since this is separable, what we can do, we're going to solve this one for v first. Okay, so there are two steps. Now what we can do, solve for v first and then solve for y, then solve for y. So that's the main technique. So what we can do, we use a special substitution, or a direct substitution. That direct substitution bring the problem to a separable equation. Once you bring it to a separable equation, we use the techniques learned in separable equation to solve for v first. Once you solve for v, what we can do, we can substitute, we can replace that v by x minus y plus 1 in this case, and then you can solve for y. Okay, so let's do this in a real problem. So so let's do that. So let's solve like easy one first. So how about this problem? So example number 1, solve y prime equal x plus y to the square. So what's the inside function for this problem? So you can see that the inside function is x plus y. So right, so that's the inside function. So we're going to call this v. Okay, so the answer, so let v equal x plus y. It is always the inside function. And once you do that, then by differentiating, we're gonna get v prime equal 1 plus y prime. This says that y prime equal v prime minus 1. Substituting, okay, we're gonna substitute. Then what will happen to the differential equation? It become v prime minus 1 on this side. The other side simply become v squared. Okay, we can rewrite this one as v prime equal 1 plus v squared, and you can see that this is a separable equation. This is a separable equation. So what we can integrate the two sides, because you can write this one as dv over dx, so it's separable. So we can do integrate. Okay, we can integrate. Once you integrate, what will happen, we can first rewrite as dv over 1 plus v squared, the other side is dx, so we can integrate the two sides. And this is the 1 plus v squared means a tan inverse, so this is going to be a tan inverse v, and this is x plus c, the constant. So if you take the tan both sides, we're going to get tan, here it get cancelled, so you're going to get tan x plus c from trigonometry. Okay, so this is the general solution, but now what we can do is we can replace that v by x plus y. So we can say since v equal x plus y, we're gonna get x plus y equal tan x plus c. In other words, this is that y equal tan x plus c minus x. So that is the general solution. So you can see that it is not that difficult, but you need to use that special substitution v equal x plus y, the inside function. Okay, so this substitution make all these happen. So the substitution bring the problem from difficult to a separable equation, and then we know how to do separable equations, so we can use that technique to simplify solve the problem. Okay, so let's go back to the problem that we were talking about at the beginning. Okay, so we can do that now because that's a little complicated. Okay, example number 2. Solve y prime equal x minus y plus 1 to the square. So the answer, let v equal x minus y plus 1. Then we have v prime equal 1 minus y prime. So this can give you y prime equal 1 minus v prime. So then the differential equation becomes 1 minus v prime equal v squared. Okay, so this one you can write as, so you can bring v prime to one side, so then you can write this one as dv over dx equal 1 minus v squared. So you can see that this is a separable equation. So so this is not easy. This is not that difficult. What I did was, like, I just move the y prime, v prime, v squared to the other side, and then multiply by the negative sign. So you're gonna get this one. So there are a lot of ways to get this answer. So now this is separable, and what we can do is we can integrate two sides. So I'm gonna call this equation equation star, because we're gonna refer this later. So what we can do, we can integrate, so this is separable, so you're gonna move the terms around and integrate. So what we do, we can write this one as dv over 1 minus v squared, and this side is dx. Now what we can do, we can integrate two sides. Okay, integrate two sides. Okay, now the question is how to integrate that. One side is easy, this is just x plus c, so that side is easy. So what about the other side? How to do the left side? To do the left side, you can see that you can factor the denominator very easily. Since you can factor the denominator, what you can do is you can use the partial fraction method. So we can use the partial fraction method. So use partial fraction method. Partial fraction method, or a formula learned in Calc 2, or use or formula from Calc 2. So, and if you forget what is the partial fraction method and how to do certain problems, so there's a video in Calc 2, so you can watch that video, and there are like about 6-7 problems solved in there. We know that there are 3 major types, and there are enough examples to learn how to do it properly. So, so I'm going to recall some of those formulas for you. So let's see what are those formulas from Calc 2 that we need for our purpose. So I'm going to write them in 1. So it's easy. So what are the formulas? So we have, so this is simply from Calc 2. So what are those formulas that we learn here? So what is one formula is the 1 plus x squared formula, or you can say like I'm going to write it like that. A squared plus x squared formula. So this we know, if we have a squared plus x squared, it is simply 1 over a tan inverse, or the arctan x over a plus c. That's the first equation. And the second equation is that we need for our purposes, it is dx. What if you have a negative sign instead? So when you have x squared minus a squared, if you have a negative sign like that, so what we normally do is we're gonna use the partial fraction method. So partial fraction method, if you use the partial fraction method, you can get the final answer as 1 over 2a natural log x minus a over x plus a plus c. So for this class you can use this as a direct formula, but in Calc 2 you have to prove this. And what's the other formula? What if you're going to change the order? So you write a squared minus x squared. So what's going to happen is, in this case again you can use a partial fraction method to get this one. What will happen is a negative sign. That means in the natural log you're going to make it upside down. So it's going to be x plus a over x minus a. So that's what happens. So it's just make upside down. So those are the 3 formulas that are important for us. So I'm going to write here can be proved by partial fraction method. Okay. So can be proved by partial fraction method. Partial fraction method. Okay, and this was given as formulas in Calc 2. We prove this one in Calc 2 when we do partial fraction method, but now you can use this as a formula. So okay, so now we can use this formula to write our solution. Okay, so we need third equation for us. So let's go back, and what we have is, you can see dv over 1 minus x squared, in this case a equal 1. This is v is acting as x, so that means we can directly write this one. Or the other way is you can use a partial fraction method to do it, And if you use the partial fraction method, I'm going to write what you really need here. So you can see that we have 1 over 1 minus v squared. We have nice factors here, so we can write a over 1 minus v plus b over 1 plus v, and then we can find a and b. And you can see that if you find a and b, you're going to get 1/2. One is 1/2, one is negative 1/2. You simply end up getting 1 over v plus 1 minus 1 over v minus 1, and you can see that these are very easy to integrate. That's why you get the natural log. Once you integrate this, you get natural log. So that's exactly what happened here, but you have the formula right now, so you can directly use the formula. So let's finish the rest of the problem. So now what we know what's going to happen to the left side now using the formula. Now you can write this one as so what we have is again dv over 1 minus v squared dx. So we integrate two sides. So what happened? So using formula, or the partial fraction method, one of them, you end up getting 1/2 natural log. So this is the 1 minus case, so it's a plus 1 comes to the top, so it's v plus 1 over v minus 1 equal x plus c. And now what we can do is we can write this as the log form. So when you write this as the log form, v plus 1 over v minus 1 minus v minus 1, so v minus 1 equal, or we remove the absolute sign, so plus or minus e to the actually we first multiply by 2, so we're gonna get 2x plus 2c, because you multiply by 2 first and then write the exponential form. So I think this is clear. Now this one is, you can write as, so we have done this several times, e to the 2c and then e to the 2x, and then by abuse of notation I'm just going to call this is c, okay, the whole thing. So it is c e to the 2x. So up to now I think it's very clear. Now what we can do, we're gonna consider two cases. So what cannot happen, for example, v cannot be 1, because if v is 1 we are dividing by 0. And also on the other side, you're going to see in general exponential function that's never going to be 0. So maybe we also assume that v is not equal to negative 1 as well. So those two are the assumptions, and then let's see what we can do with that later. Okay, so so what we have, so note that v equal plus or minus 1 are solutions of the original equation. So what the original equation that we have? So so if you go back, remember we call this equation star, and you can see when you plug in v equal plus or minus 1, it's gonna work. That means plus or minus 1 are solutions of this equation. Okay, so we're gonna come back to that later. So that means so we know that those are solutions, so we assume that, so we know that these are solutions, so let's try to find the other solutions. So that means now let's assume, okay, so assume that v are not equal to plus or minus 1. If v not equal to plus or minus 1, then we can write this equation, v plus 1 over v minus 1 equals c e to the 2x. Now what we can do, so we solve for v, so just v equation. Now what we can do is we can substitute the x plus y. So since v equal x minus y plus 1, that was a substitution. Now we're going to substitute back here. So if you substitute that here, you're going to get x minus y plus 2 over v minus 1, that means x minus y equals c e to x. That's what you get. Now what we can do, solve for y. Okay, so solve for y. Solve for y. How to solve for y? You can cross multiply first. Once you cross multiply, you're gonna get x minus y plus 2 equal x minus y times e to the 2 e to the I forgot the c, e to the c e to x, and if you distribute c x e to the 2x minus cy e to the 2x. Now bring all the y terms to one side, so it is cy e to x minus y equal cx e to x. So y terms on one side, x terms on the other side, and minus 2 as well. Now what we can do, we're going to take y as a factor and divide. So you're going to see y equal cx e to x minus 2 over the factor is c e to x minus 1. Perfect. So that's the y. So but we still so this is not the final answer, because we still need to know what's going to happen with y v equal plus or minus 1. So we're going to consider those two cases separately. So let's see what's going to happen in each case. So if v equal 1, you're going to get x minus y plus 1 equal 1. This is going to give you y equal x, and you can see that this satisfies the original equation. Okay. If you go back to the original, so we need to check the original equation. Okay, so so we can check the original equation. We can substitute this in the original equation. Check the original equation. So if you substitute the original equation, you can see that it can work. And also let's check the other one. Okay, so if v equal negative 1, you're going to get x minus y plus 1 equal negative 1. This is going to give you y equal x plus 2, and you can see that this also going to work in the original equation. So that means these two going to give you two other solutions. So the solution to y prime equal x minus y plus 1 squared so there are a lot of solutions. Y equal x, that's one solution, or y equal x plus 2, okay, or y equal the last one that we get, cx e to x minus 2 over c e to x minus 1. And so these solutions are, the first two solutions are what we normally call singular solutions. So these are the singular solutions. Okay, the other one is a non-singular solution. Good. So this is the final answer for this problem. Okay, so so you can try this problem. So this is an exercise for you to try. So exercise 1. So solve the initial value problem. So let's say dy over dx equal y minus 2x squared minus 7 along with y0 equals 0. So there's the initial condition as well, so you can check what can satisfy that. Okay, so the solution to this problem will be in the description. Okay, so so for example here this c, see there are c's here, and then we're going to find them. So use initial conditions to find them. Okay, so once you plug in the initial condition, and you can solve for c. Okay, good. So let's do one last problem. So this is the last one. So example number 3. Solve. I don't want to star here because it's a different type. Solve 3y squared y prime plus 3 equal y cube plus x. So you can see that this problem is slightly different from what we did before, especially the term here. So there's a y squared y prime. The reason is y is a function of x, so if you take the derivative by the chain rule, you have to multiply by y prime. So that's exactly the reason. So that means it's going to tell you what to do. So what we're going to do, looking at the derivative, is clear that we need to take let v equal y cube. Okay, so that's the starting point. Once you use this substitution, everything gonna work very well. So then if you take the derivative of both sides, this become dv over dx, and here what we need to do is we need to take the derivative of v with respect to y first, and then dy over dx. So that means by this is the chain rule. Okay, and then what's going to happen, this is going to give you 3y squared dy over dx is y prime, and you can see that this term is sitting there nicely. Okay, sometimes you might not 3 at the beginning, but here you actually see 3 here, so things are easy. Okay. So that means you can replace 3y squared y prime by simply v prime. So we can write this equation as now as v prime equal 3y squared y prime. So what we can do, we can substitute for both sides. Wherever you see y cube, you can substitute v. Wherever you see 3y squared y prime, you can substitute v prime. Okay, so by substituting, so we can substitute now. So substituting, okay, substituting, we can have v prime plus 3 equal v plus x. Now we can move the terms around, so you can see that this is v prime minus v equal x minus 3. So this is a first order linear or the integrating factor problem. So this is first order linear. First order linear, so we can use the integrating factor method. Integrating factors. Okay, we can use integrating factor method. So once you use integrating factor method, so what's the integrating factor here? So I equal e to the negative x, negative dx, not negative x, negative dx. That means e to the negative x. So that's the integrating factor. So that means this simply becomes d over dx, v and the integrating factor. On the other side, you're gonna get x minus 3 times e to the negative x. Now what we can do, we can integrate. When you integrate, you're gonna get v e negative x, the integral of x minus 3 e to the negative x dx. Okay, so so for the right side, you can see that this is a partial fraction integration by parts problem. This is integration by part problem. So what we can do, we can use the tabular method here. So there will be there is a separate video to learn about the tabular method, or what sometimes we also call the DI method. So watch that video to learn more about the DI method. Okay, so there are about 6 different examples solved in there, so you can learn that. Okay, so let's go to the technique. If you forget, if you don't know, so we got d and I derivative and the integral. So what we can do, we're gonna take x minus 3 to this side. So all, if you see a polynomial, we normally put the polynomial on this side, and this is e to the minus x. So what we do, this side you take the derivatives until you see a 0, and the other side you take the integral at the same time. So that's the first starting with. So you can write that and that. So you're going to pick those two terms and put it there. So take the derivative. So it's a 1. Take the integral, negative e negative x. Take the derivative 0. That means you stop. So that means you only need one more term. So it is negative e to the negative x. So those are the terms that you need. You take the derivative of the left column. You take the integral of the right column. That's the di, derivative and the integral. Now what we can do, interesting. We're gonna multiply these two terms along the diagonal. So that's how it's gonna go. And when you see 0, you stop. And also you always start with a plus sign and then a minus sign, and alternatively you change the sign. You always start with a plus sign. And this is gonna, so what you do, you're gonna multiply across the diagonal along with this sign convention. So you're gonna multiply the terms along the diagonal. So that means if you use that argument, your final answer would be, you're going to multiply and with the plus sign, so it's going to be negative x minus 3 e to the negative x. That's the first term. And then minus that term. You multiply the other two. When you multiply these two, you will get e to the negative x and plus c. So that's the answer. So you can write this directly like that, but you need to show the work like this. So the di method works very easily like that. So you take the derivative of the first term and the integral of the second term, and then you multiply across the diagonal. Always start with the plus sign. Okay, good. So you are allowed to use this technique for this class. Okay, so not in Calc 2, but now you can use this because now we know what we need to do. Okay, so we need to do some simplification. So what to do next? I'm going to multiply both sides by e to the x. So if you multiply both sides by e to the x, you're going to get v equal. If you multiply e to the x, e to the negative x get cancelled, so you're going to get c e to the x, and then you're going to get negative x negative plus 2. That's what you get. Okay, now what we do, we're going to substitute for v. Okay, so since v equal y3 equal cex minus x plus 2. This, if you take the cube root, you end up getting y equal cex minus x plus 2, the cube root. Okay, so that's the final answer for the problem, and you can see that it's not that difficult, but still there are certain things that you need to remember. Good. So I'm going to give you a table of substitutions that you possibly use for these kind of problems, especially for the last problem. So let's do that, and that's the end of this. So the possible substitutions. Possible substitutions. Possible substitutions. So let's say when you see, try the substitution. Try the substitution. So when you see y prime term, so the substitution would be, because that should be the derivative, we're going to say v equal y squared. Okay, because if this is the case, what's going to happen if you take the derivative, v prime equal to y prime, and then you can solve for this. So it's going to be half v prime. Okay, so you're going to solve for that. So you're going to substitute half v prime. Good. And then when you see y squared y prime, we're going to say v equal y3. We just saw that. And also if you forget, this is coming from the chain rule. Okay, so it's coming from the chain rule. And then we have other types. For example, you have cosine y, y prime. I'm going to write y prime in front just to avoid the confusion. And in that case, v equal, because it's a derivative, v equals sine y. And if you see y prime sine y, we're going to say v equal cosine y. And also you might see e to the y, y prime. If you see e to the y, y prime, it is v equal e to the y, because it's clear. If you take the derivative, what's going to happen? We have e to the y, y prime. That's what you get, again from the chain rule. Also, you might see some terms like that, especially in the homework. V squared plus or minus, either plus or minus sign. If you see something like that, just pick the whole term as v. So we can say v equal whatever the term that you have, and then just do the way we do it. Okay, so these are the kind of common substitutions that you might need. So I'm going to give you this problem for you to try, and you're going to see the answers in the description. So this is exercise number 2, because I want to refer to this. So solve. The first one is y prime sine y plus 2 cosine squared y equal to, and b e to the y prime equal x plus e to the y along with y0 equal 1. Okay, so try these problems, and you can see the answers in the description. Thank you.